Hi everyone, and welcome back to Fresh Thinking, the podcast where we take ideas that can sound pretty intimidating on paper and unpack what they actually mean for day-to-day geology, mine planning and resource work. I'm Jamie, Senior Consultant here at Snowden Optiro, and today we're talking about a word that's been popping up more and more in geostatistics, in machine learning workflows, and in conversations that sometimes make people quietly nod along in meetings. Convolution. If your first reaction to that word is, oh, that sounds mathematical, don't worry, we're keeping this really grounded. We'll be talking about blocks, grades, trends, search neighborhoods, and the kinds of decisions we make every day on site or in front of a block model. To help with that, I'm joined by Greg, Senior Consultant, who many of you probably know for his work in advanced estimation and for his ability to explain genuinely complex ideas in a way that actually makes sense. Thanks, Greg, for joining me.
Thanks, Jamie. I'm excited to talk about how a simple moving average, kriging, residuals, and even convolutional neural networks that can fit into one coherent workflow.
Great. So let's start by zooming out for a second. If we've got something like copper grades measured along drill holes, what we see in the data is actually a combination of things. So we've got broad geological trends, plus a lot of local noise and short-scale variability. And in practice, this is usually where teams start to disagree about what's real geology and what's just local variability.
Yeah, that's good. So think of the observed grade at location as two parts. So the first is a smooth trend, which it shows us the regional structure, and maybe it's stratigraphic, it's intrusive bodies or depth-related effects. And then it's a residue. Residue can be more local structures, could be lenses, veins, or short-range variabilities. So overall, the observed grade equals the global trend plus the local residue. And then detrending is about estimating the trend first, and then subtracting that from the observed grade, so we can get the residue. And then we can model that spatial correlation of the residue and then add that back on top of the trend, then that will get our estimated grade. So in geostatistics, this is close to universal kriging. And operationally, a lot of teams do that trend first and then residue second.
Okay, and the key idea today is that the moving average can act as a deliberate, defensible trend model, not just a quick smoothing trick.
Exactly. So moving average is just a convolution, a very simplified convolution with a smoothing kernel. This kernel can be a uniform or Gaussian kernel. Window, you slide that window around across a space and averaging whatever is inside. And that gives us a local background level. And that background becomes your trend.
Convolution can sound like a big concept. Can we explain it in a more practical way?
Sure. So picture a transparent stencil and then your kernel, which laid over the map. It has weights that sums to 1. And then you'll place it on a location and multiply nearby values by those weights and then add them up. That's one smoothed value. So slide that stencils across the map and then you will get the smoothed value everywhere, and which will constitute a surface. So that's a convolution.
So a moving average is the stencil where every pixel inside the window gets equal weight.
Right. If you choose a Gaussian kernel, then nearby samples can get more weights and then the further ones, and which is often nicer for the geology because trends are usually very smooth. And then also if you want to put some declustering at first, then in that case, when you do this moving average, you are also considering the declustering as well. So that's another way to add some complication on top of the naive average.
Uh-huh. And how do you choose your window size?
Well, there are two pragmatic options. So the first is related to the variogram. So we could choose a kernel window near or slightly larger than the range of our variogram, or short scale structures. So if the goal is to capture the broad trend and leave the short range correlation to the residuals, which we'll deal with that later on. Or we could just use cross validation. So we can test a few window size and then keep the one that get you the best residual model performance downstream.
Okay, so we've got our trend from the moving average. We subtract that from the observed grades, and then we're left with the residuals. What happens next?
Then we could analyze the variogram of the residues, and now they should be closer to stationarity. This stationarity is a very, very important assumption for most of the kriging methods. So theoretically, if the domain doesn't have enough stationarity, then it shouldn't be used with kriging methods. Then with the residue at this stage, if we've done everything right, and then now the residues should have enough stationarity, and then that's perfect for the kriging. And so fit a variogram model, then often nested structures with an isotropy, with if geology has some preferred direction, and then we can perform ordinary kriging on the residues and get that R value. Finally, we can add that on top of the trend, and then that will be our predicted grade.
Mm-hmm. So the moving average convolution strips out our broad regional trend, and then kriging focuses on what's happening locally, the spatially correlated detail that we actually care about during estimation.
Yes, that's right, and it's a divide and conquer strategy.
Okay, so the convolutional neural networks, CNNs, also use convolution. Is this reality just a fancy moving average? And from your experience, where is the point where CNNs stop adding value and start adding risk?
Good question. So CNN, they are a learned version with depth. Instead of you choosing one moving window size, CNN can learn many filters simultaneously. So some smooth, some edge effect, and some oriented to the geology lineaments with multiple input channels. Say, for example, we can have multiple grades, and we can have alterations, we can have lithology structure, or some other numeric or non-alphanumeric values, where the goal is that by using CNN, it can learn those nonlinear correlation and then mapping that to the target grade.
So kriging formalizes spatial correlation using a variogram and gives you uncertainty.
Right.
CNNs, on the other hand, can take in a much more mixed set of data and learned patterns, things like contacts, faults, or textures, without you having to hardwire them.
Yeah, that's a trade. So CNN shines with rich covariates and enough labeled data, but they don't naively give unbiased uncertainty the way kriging variance does. And so they are vulnerable to the spatial leakage if you validate naively, and you need a spatial block cross validation and careful train test separation in space to make it work.
Okay, so can we run through a step-by-step process that a mine geologist could actually use this quarter with the data that they already have, rather than, like a blue sky rebuild?
Sure. So there'll be two passes. So one's classic and the other's deep. So the classic one will be convolution to get the trend, and then plus the kriging for the residues. So what we could do is we could find the area of the interest, we could assemble our composites at the target support, whichever is block level or size we're interested, 25 by 5. And then we can convolution to get the trend. So we could choose a kernel size, tri-field size maybe, and then to also do the cross-validation. This essentially is a cross-validation, and then get that trend. Then we could calculate that the residues. For example, we can get the target value minus trend to get our residue. Then we can do the variography on the residues. We could check the anisotropy and then fit the nested structures, like what we do most of the time when we do the variogram modeling. Mm-hmm. Then we could do the ordinary kriging or simple kriging on the residues. Then we get both our kriging residue and the kriging variance. Then we can add this kriging residue on top of the trend. We get our estimated grade. And then we could do some further cross-validation. We could take some blocks out and samples. Then we could just run the estimation, then compare how that works. Usually we could call that jackknife test, but different areas, they have different names. Essentially, they have the same logic. Mm-hmm. So this is a traditional way or classic way. Then for the more complicated way, that is CNN for the nonlinear multi-source mapping, that we could stack multi-channel information. For example, geology, we could use categorical coding, or in data science, maybe it's called one-hot coding, that you can convert whatever is alphanumeric values into that categorical values. Then we could add the grades, the distance to the boundaries, or any geochem information in there. So the second part is the CNN for the nonlinear multi-score mapping. So the first, we could stack multiple channel information together. That could include our alphanumeric values, for example, the lithology alteration, plus some grades, maybe multiple grades, even the full suite of the geochems, and plus some distance to the contacts. Then we could do the patch sampling to split the data into the train and evaluation data sets. And then we could train very shallow CNN to predict the grades, including dropout, for that rough epistemic signals of the train ensemble for the uncertainty analysis. Then optionally, we could hybridize. We could use convolutional smoothing to estimate the trend channel, and then let the CNN learn that residue-like detail relative to that trend. Then we can compare against the kriged residue workflow on the same block folds, and or potentially with some other methods to essentially taking that as a check estimate.
Okay. Well, that sounds great. What I really like about this is that it doesn't force you into an either or choice. Sure. You can stay grounded in variograms and kriging, but you can still make use of richer data sets where you can genuinely add information. So to wrap up part one, we really focused on the foundations. We talked about what we actually mean by detrending, why convolution doesn't have to be complicated, and how something as simple as a moving average can be used deliberately as a trend model. We then walked through how detrending and kriging work together, using convolution to handle the broad geological picture and kriging to honour the local, spatially correlated detail in the residuals. And finally, we laid out a practical step-by-step workflow that a mine geologist could realistically run with the data they already have, without needing a complete rebuild of their model. In part two, next time, we're going to build on that foundation and look at how these ideas extend into hybrid workflows, including where convolution shows up in machine learning approaches, how to combine richer data sets like magnetic and structure, and where the real pitfalls are.